Hello, and welcome to my short pre-recorded talk where I'll be discussing a stochastic model of chemorepulsion with additive noise and nonlinear sensitivity. Before I get started, I'd just like to thank the organizers for the opportunity to present this work and you, the viewer, for taking the time to watch it. So in this talk, I'll be presenting some joint work with Ilya Chevarev and Ben Hambley that was carried out while I was at the University of Oxford. And there's an archive preprint available where you can see a full preprint of the paper. So I'll be talking about a stochastic model of chemotaxis, specifically a model of chemorepulsion. So more generally, chemotaxis refers to microorganisms, maybe single cells, automata, or amoeba, that kind of thing, undergoing directed movement, typically directed by some self-generated chemical field or potential field we can think of. So some examples would be white blood cells during an immune response. Some amoeba behave this way under certain starvation conditions. But we could also imagine sort of fleets of self-organized drones, or even crime hotspots have been modeled in this way. There's a very comprehensive overview by Painter referenced here, which gives a load of examples. So some work in the 50s and 70s by Patlak, Keller, and Siegel derived some PDE models that have been very fruitful in studying this situation, and the work I'm going to present is based on those ideas. So if we think about the PDE setting to begin with, the model originally presented by Patlak, Keller, and Siegel can be thought of as a system of parabolic equations where we have the first equation U modeling what we typically call the cell density, so that's the agent density, and rho here representing the density of the potential. So we can see in this system, the potential observes the cell density as a forcing term. So the cell density generates the potential term. And the coupling occurs here through this transport term and through this possibly nonlinear term in here. This is what we'll call the nonlinear sensitivity. So we can classify chemotactic models into two regimes. The chemoattractive regime, which is where the nonlinearity is negative for positive cell density. So essentially cells will be pulled towards each other. And the chemorepulsive regime, which is where the nonlinear sensitivity or possibly linear sensitivity is positive for positive cell densities. So their cells will be repelled from each other. And one other observation we can make that has been made by a number of authors is that it's natural to assume that the chemical density will diffuse far more rapidly than the cells. So if we think of the chemicals as sort of being a molecular scale and the cells as being cell scales, then the chemical density will diffuse far more rapidly. And this justifies simplifying the model somewhat by setting the diffusivity parameter here to be 0 in the chemical equation. And this reduces us to what's known as the parabolic elliptic Keller-Siegel system. So we have the parabolic equation governing the cell density and an elliptic equation governing the potential. This simplifies the analysis somewhat and is also justified by some simulations, although of course the full parabolic model is richer and has more intricate behavior. So we'll be working with a parabolic elliptic equation from now on. So while these PDE models capture a lot of the behavior of chemotactic systems, it's also natural to imagine that they might take place within complex environments or in the process of other possibly random processes. So just to list some examples, we might imagine chemotaxis taking place in the presence of maybe some turbulent ambient fluid, maybe inside another organism or in a body of water or something like that. Fluctuating population size, this can be because of growth and death effects in the population if they're organic organisms, or sort of random failures, that kind of thing in other organisms or other agents. Also, it's usual to think of these PDEs as really being approximated by particle systems as being statistical representations of some large particle system. And it's also natural to think that when the particle number is very low, there can be random fluctuations around the PDE limit. And so that can lead to stochastic terms appearing in the modeling or analysis of these questions. And secondly, we might imagine this sort of random effects happening in the chemical production or sensitivity. This is all just to say that studying SPDE models of chemotaxis is a fairly natural question. And so a general form of these models, a very general form that would be too difficult to analyze in full generality, would be to introduce stochastic terms, noise terms, depending on the cell density and the chemical density in the first equation, and maybe a second term also depending on the three parameters and an additional source of noise in the potential equation. And so in this notation, I'm just thinking of two sources of noise, and some representatives for these nonlinear terms are given down here. So we might think of just purely additive noise, or a transport type noise, a multiplicative noise, sort of as in the Anderson equation, Anderson Hamiltonian. A Feller type noise, this would typically be used for sort of fluctuating population sizes, or this a sort of divergence of the square root of u times a noise, and this comes from some ideas of Dean and Kawasaki regarding low particle fluctuations. So in this talk, I'm only going to be thinking about additive noise, so we can see that we're missing out on a whole range of complicated noise terms we could consider, but I'll hope to convince you that the additive noise regime that we do consider is at least a good starting step for some of these more singular and more problematic noise terms. So onto the model that we actually consider. So we'll be working in one spatial dimension only, and we'll be thinking about a parabolic elliptic model of chemotaxis, where, as I mentioned on the previous slide, we'll consider additive noise, in this case space-time white noise, and the nonlinear sensitivity function that we choose is just u squared. So in the previous general form of the equation, we had f of u and rho, and here we'll be specifying down to the nonlinear sensitivity being u squared. And this PDE model of chemorepulsion was actually previously studied both by Tao in 2013 and Lai and Zhao in 2017. And they proved some results also in one spatial dimension regarding well-posedness and an a priori bounds on this equation without the noise term. So some features of this model. So it contains chemorepulsion. So that means that the cells are induced to move away from each other. And this suggests also that we should obtain global well-posedness, and the nonlinear term should allow us to damp out the sort of rough forcing coming from the noise, and this is what we find. The chemosensitivity is quadratic, which means since rho is really a function of u, this whole term is cubic. And so later I'll make some comparisons between our results and known results for stochastic reaction diffusion equations, which have a similar nonlinearity. And as I mentioned already, we have additive space-time white noise. So some comments on the noise, because it is a little unusual. So firstly, from a modeling perspective, as I said, there are many situations where the equations of chemotaxis can be used. And so for many of them, it does make sense for the solution U to preserve sign and mass. However, there are situations where we might imagine there could be random fluctuations in the population size, members of the population is dropping in and out, and that is something that an additive noise would certainly capture. It would be more accurate to modulate the noise in that case by the square root of u, as in Feller noise. But as I said, in this case, for this work, we'll be sticking with a simpler noise that we can analyze very fully. And this leads me on to the second reason for considering additive noise, and specifically additive space-time white noise, is that it also allows us to simplify the ergodic theory of this equation. Before we move on, I just want to mention that alternative stochastic models of chemotactic equations have been studied by Flanderly, Galeatti, and Luo, and Huang and Chu, and Misiat, Stanizhitsky, and Topologlu in some work cited here as well. So to our main results, we obtain two main results on our SPDE model. So the first being global well-posedness, which, as I said, we expected as a consequence of the chemorepulsive nonlinearity that we chose. So we find that for any initial data living in any space more regular than C minus 1/2, so these are scales of Holder-Bessel spaces on the torus, can be defined by Littlewood Paley blocks or local averages, then we find an almost sure, so a pathwise solution, a unique mild solution living in any space more regular than C1/2, less regular, sorry, than C1/2. So any space with Holder space with parameters less than C1/2. And we also show preservation of mass, provided that we choose the noise to be mean free. So it integrates to 0 on the torus. And the second result we find is exponential ergodicity for this SPD, or really for its associated semigroup. So we find a unique invariant measure with full support in the solution space so that for any initial data, we have exponential convergence in total variation norm of the law of our solution to the invariant measure. And we also find tail estimates. However, these tail estimates are strictly sub-Gaussian. So if we measure the solution in any LP norm, the invariant measure has finite exponential moments with weight strictly less than 1, even in this case, so even way less than 2. So this is an interesting point of comparison that I alluded to before with stochastic reaction diffusion equations. So if we consider a very simple stochastic reaction diffusion equation, for example, one that's been studied in a paper by Moynat and Weber in 2020, with just a minus u cubed nonlinearity. So although this paper does not concern itself with ergodicity of the system, it is known that this system is exponentially ergodic. But what's relevant for us is that Moynat and Weber were able to establish, using the a priori bounds that they find on the SPDE, very strong tail estimates on this solution. So in fact, in one dimension, they find that the solution, or an invariant measure to this equation, would have super Gaussian tails, so exponential moments with parameter strictly larger than 2. And this is in contrast to what we found. And what's interesting is that if we expand our nonlinear term, remember this is the nonlinear sensitivity term that we had, we find minus u cubed. This comes from when the second derivative hits rho, which produces a minus u, plus a quadratic term multiplied by the mean of u. This can be absorbed by the damping of minus u cubed, so that's no problem. But however, what causes an issue in our analysis is this transport term. So you can read this as a sort of nonlinear transport term of u squared by the potential rho. And we find both in establishing a priori bounds and bounds on our invariant measure, on the tail estimates for our invariant measure. And this term is the term that causes problems and results in the lower, the sub-Gaussian tails that we have. So we think this is quite interesting, that it shows this, this very rough transport term is affecting the integrability of the invariant measure. So before I run out of time, I just want to talk a little bit about some directions that would be nice to extend this work. So from the perspective I just highlighted, it'd be really interesting to see if we can obtain similar results for higher powers, higher order nonlinearities. So some initial work suggests this might actually be quite problematic, but it'd be interesting to see if it's possible, maybe using other techniques. Secondly, I've so far been talking about the chemorepulsive regime, and of course it'd be natural to study the chemoattractive regime as well. So a natural candidate there, for example, would be to take minus the absolute value of u if we're considering additive noise. As I said, this won't preserve sign, so we need to do something to preserve the sign in the nonlinearity. And again, some initial work on this suggests it's quite a difficult problem. So thirdly, as I alluded to at the beginning of the talk, there are obviously a wide array of noise terms that'd be interesting to study. And some of these have already been looked at by other authors, as I mentioned, but developing more analysis of these models and their effects on say, the invariant behavior of this equation would be very interesting. And finally, of course, I've only been looking at a one-dimensional model, and some higher dimensions would be very natural. 2D is a very natural setting for chemotactic models. So finally, I just want to say that all these advances present significant challenges as far as we're aware, but they would certainly be interesting to study. So finally, I just want to thank you for your attention. Happy to answer any questions in the open session, and here is a list of some references that will be available in the slides as well. Thank you very much.